Hello and welcome again to our review of operating systems with the Cyber Professor. I want to make sure that we review the course map for the operating systems course that we are conducting. As you may remember, the way that we are conducting the review of operating systems is by first talking about the introduction to operating systems. We completed that portion a couple of weeks ago. Then we moved to number 2, which is processor management. And processor management is covered in 3 chapters of your textbook, chapters 4, 5, and 6. So today's session is going to cover chapter 4 and the first half of chapter 5. So that will be the goal for today's session. And then next week, what I envision us doing is completing the review of chapter 5, the second portion of chapter 5, and then complete the review of chapter 6. And when we do that next week, we are going to be in a position to finish the review of number 2 here in our course map, processor management. Moving right along, the objectives for chapter 4 are as follows. What is a program, process, thread, and process characteristics? That will be objective number 1. Objective number 2 is what are process control blocks or PCBs, process and context switches. Objective number 3 will be our review of process and CPU scheduling, as well as preemptive and non-preemptive scheduling. And finally, objective number 4 will be the scheduling criteria and algorithms, which is the topic, the last part of the processor management chapter in chapter 4. Definitions. So this is an important component of our review. I want to make sure that we are all on the same page as far as the definitions that are used during this review of process management. We want to make sure that number 1, we have the same common understanding of the components of process management. So first, let's talk about program. A program is a software typically written in a high-level language, like, for example, C++. A program is what software developers or programmers write, is the code that is written by the software programmers, and we need to take a look at it from the perspective of the program being the passive component. Rather than the active one. So for the active one, we move to the second concept of our definitions, and that is the process. So a process can be defined as a program under execution in RAM with resources allocated to it. And you may ask, what are those resources? And the answer is the resources that we are talking about are CPU, the processor, RAM, the memory, and input and output devices. So from that perspective, we need to take a look at it as the unit of execution. The process is a unit of execution, and the process is the active component. So we talk about programs first. Program is the passive component because it's just the code that is written for an application, a software application, and once we move that code, we compile that code and we release it for distribution. Then it becomes a process once we load some of those steps into memory and we allocate resources to those processes that are part of the program. So the way to do it is you need to grab the program written in high-level language and then compile it to help convert that code into binary machine code that is understood by computers. So for those of you that are take in some of my networking classes, we talked about the way that computers understand instructions, and we talk about binary code being the way that computers can understand some of the instructions that we as the users provide to those computer systems. So in order for the program to be understood by the computer system, it has to be compiled and converted into binary machine code. And these converted instructions need to be loaded into memory for execution. So the operating system is responsible to execute those instructions in the form of processes. A program is the code you write, and the process is when you take the program and you start executing it. So that is why we see the process as the active component. Now, thread, we move to the third definition in our table here, and we talk about thread. A thread is the unit of execution within a process. So a process can have anywhere from one to many different threads that are part of the same process. So within the process, you may see multiple threads. Multi-programming is another concept that we need to understand to be on the same page, and multi-programming requires that the processor be allocated to each job or to each process for a period of time and then deallocated at an appropriate moment. Finally, we move to the last concept in our definitions, and that is the process control blocks. Each process is represented in the operating system by a process control block, PCB, also called a task control block. So PCB is a data structure that stores all of the attributes of a process. Look at it as a database or a database record. So the process control block is a database record that has different components that are describing the elements of the process. And the operating system, that is the connection with the topic that we are studying in this course, the operating system is responsible for maintaining that database record or records and making sure that they are clearly identified, so then the resources that are part of the computer system, CPU, memory, input and output devices, can be allocated to those processes that are part of the different activities taking place in a computer system. So again, these are important definitions for you to understand and remember, not only for this course but throughout your career in technology. So again, we mentioned that beginning with a program, which is a set of written code, we move to the process, which is the active component of a program, because we are actually grabbing some of the instructions that are part of the program and putting them or loading them into memory, so the computer can process or execute those instructions as part of the program activities. So that process that we are discussing today is made up of one or more threads, and that is the picture that we are describing here, that we are depicting here. So we have a process with multiple threads. And just so you understand the real application of these concepts, let me do something for you. So let me do a Control-Alt-Delete on my computer, and then we move to the task manager. So within Control-Alt-Delete, we are able to, in the meantime, let me start one of the VMs really quick as well. So in our Windows 10 computer system that we are using for this presentation, my laptop in this case, we do a Control-Alt-Delete and then we go to Task Manager by selecting Task Manager from the Control-Alt-Delete menu. And then under Task Manager, we see in the main menu, Processes is one of the options. So as you can see, there are many processes that are running on my computer, and they are listed by name on the left column of this window that I am displaying for you. So you can see the name of the process, we can see the type of process, we see the publisher of the process, and this is an important component, the process ID or identification number that is listed in this column here, the one that I am pointing at with my mouse, the process name, the command line, and this is another component, important component of what we are discussing today, which is the allocation of those resources for the processes. So now we are bringing the concept into life. We want to make sure that we continue our approach of explaining the concepts that are important to you and important for your learning. However, we bring them to life, something that you can relate to, something that you can visualize. In this particular case, the way to visualize the concept of process is to show you the processes that are running on my Windows 10 computer in the form of the list that we can preview under Task Manager here. And we can see that there are so many processes that are listed, and we can see the different types and the different allocations of resources. Remember that we said a process is an active component, and it is the set of instructions that are coming from the program that are loaded into memory and ready to take resources from our computer system. So what resources are we talking about? These are the resources, examples of the resources that we are talking about: CPU, memory, disk, network. So all of these resources are being allocated to the processes that are that I showed you earlier. So another component of the processes is, we mentioned the threads. So in the meantime, let me see if I can get one of my virtual machines to run and show you the threads, because under Windows 10, the important comment that I want to make sure that you understand is, under Windows 10 there is a process view under Task Manager. However, you are unable to see the actual list of threads, and that is because unfortunately that is not a capability of Windows 10. But let me see if I can bring up my Windows 10 VM, and hopefully I can do that for you. Let's see. Yep. So it is booting up. While it is booting up, we move towards the concept of process control block, or PCB. That is an important definition that we learned about in the previous slide, and now we are seeing the description of a process control block in the form of a block of information or data that is keeping some of the attributes or characteristics of a specific process. So we saw the list of processes under Task Manager on my computer. Now grab just one of those processes and imagine that that process has a set of characteristics or attributes that are stored in one single database record just for that process. And these are the characteristics or attributes of that process: the process state, the process ID, the program counter, the register contents, the memory limits, the open file descriptors, and other data that is specific to one single process. So for each of the processes that I showed you under Task Manager, we view the list under Task Manager together. So for each of those processes that are under Task Manager, I'm going to bring up that window one more time so you can take a look at it. So these processes that you see on my computer under Task Manager, each of them, these are the processes. This is the list of processes. So each of these processes has a process control block, which is a database record that has all of this information for each of them, each of these processes. Now, you may ask, what is a database record? So I'm gonna give you one quick example. Imagine you are a student of a college institution, and the college institution has a database record for you as a student of the institution. Now, what will be in that database record for you as the student? It will be a set of information that includes your name, first and last name, as one of the elements of that database record. Your date of birth could be the second element of that database record. Your social security number could be the third element of that database record. The program that you are registered under, for example, if you are a computer science major, or if you are going for nursing, or if you are going for teaching or education or English as your major in the college institution. So that will be the program that you are registered under. So each of those elements will be components of your database record as a student of the college institution, and that will be just one database record for you. Now imagine the college institution has hundreds, thousands of database records for each of those students that are attending the college institution, and each of them will have one of these database records with all of their information, personal information in them. The same applies with processes. The computer system is the equivalent of the college institution, and the student database record is the equivalent of the process control block for each individual process that is running in that computer system. So that is the good analogy that we can use to understand the database record, which is the process control block for the processes. And we saw that they are listed under Task Manager. Now, if we go under my VM right here, and I'm going to display that for you as well. Let me minimize Task Manager for a second. Now let me go to my virtual machine running Windows 10 as well. However, it is not my physical computer that I am displaying to you right now. This is just a virtual machine that is running Windows 10 as well. And let's see if we can do a full screen mode for a second. And now you should be able to see my virtual machine booting up as we speak. Okay, so this is the desktop of the virtual machine, and we are going to open one of the software applications that I installed on this virtual machine by the name of Process Explorer. So we are going to do a search for Process Explorer here. And it's going to take a little bit. It's going to take a few seconds because some of the resources on my computer are running low. So I already typed in Process Explorer, so that is going to open up in a second. In the meantime, let me go back to Task Manager and make sure that I am not consuming resources from my system that are not needed. So let's see. Okay, so once we close the virtual machine, we should be fine. However, in the meantime, let's try to open Process Explorer here. And that should open the application up for us. Okay, so it appears the Process Explorer doesn't want to open, so I'm gonna leave it running on the background, and hopefully we can come back to that if we are able to get it to work. So I'm gonna put it aside for a second and close. The only reason why I wanted to show you the virtual machine with Process Explorer is that we are able to view some of the threads that are running on my system on the virtual machine by using a third-party application by the name of Process Explorer. However, the virtual machine is not responding right now, so I'm gonna put it aside. Perhaps I'm going to try to reboot it and see if that fixes the issue. Going back to our presentation. All right, So the attributes that are listed in orange right here are the attributes that are used for saving the process state when the CPU is switching from one process to the other. So imagine you have a limited amount of resources on your computer, similar to what you just witnessed on my computer when I was displaying some of the information to you. You saw the slowness of the computer because I have multiple windows running on my computer with different programs, and they are consuming a lot of my resources. So you have very limited resources available to the different processes that you want to run on your computer system. So the CPU has to switch the attention of the resources of the processing power of the processor from one process to another, and then back to a different process, and then move to another process, and it has to do it so quickly. Now, you may say, how is the processor able to do that? Keep track of all the information that is coming from different processes that are running on any given system. And I show you the huge list of processes that I have running on my computer when I open Task Manager. So that information has to be handled and managed rather quickly in a matter of milliseconds in order for the computer system to continue working for you. So the operating system, and that is the reason why we are connecting the dots here, the operating system is the one that is keeping track of this database of records, the process control block, in order to make sure that when the CPU switches the attention from one process to another, the information from the process that is stopped getting the attention from the CPU is saved and tracked. So when the CPU has to go back to that process, it remembers the last thing that was conducted or executed under that process and continues the execution of the process that was stopped for a second because the CPU needed to pay attention to a different process that was demanding the resources of the processor. So these two attributes are the ones that are used for saving the process state when the CPU switches the attention to a different process. That is why they are coloring orange. Process state is another important component of our review today, and it is important because the process state provides you the information on what the process is doing at any given time, and that is one of the first element of the attributes that I have described here in the process control block. So there are 5 different process states that we need to worry about, and those are new being the first one. The first process state that we are going to talk about. So when a program is under execution, a process has to be created at any point in time. So it is loaded into memory. So the action of creating the process is handled by the operating system. So the operating system is responsible to create the process that is going to be part of the huge list of process control blocks that the computer system will be managing. The second process state is the running state, and that is when instructions that are part of the process are being executed. By whom? By the CPU, by the memory. So the process state of running is when instructions are actually being executed. Waiting, that is a different process state, and that is when the process is waiting for some event to occur. And you may ask, what event will that be? An example could be when an input-output device needs to complete something for you. One of the typical cases that you may be familiar with is when you are opening the Microsoft Office application, Microsoft Word, and you open one of the documents in Microsoft Word, and that becomes one of the many processes that is running on your computer system. Now you click on File and then you go to Print. So you gave your computer system the instructions that are part of the process that you are running of sending a print request to your printer, which is an input and output device. And at that point, the process of printing on your computer goes into waiting state, because it has to wait for the actual paper to come out of the printer, for the printer to handle the request that you made from your computer to send output to the paper that is coming out of the printer. So the printer will take maybe 5-10 seconds for the image to be printed on a piece of paper, and those 5 or 10 seconds will be the time that your process will be put in under waiting state, because it is waiting for the input-output device, in this case the printer, to finish doing something for you. Then we move to the ready state, which is the fourth state that we are reviewing here, and that is when the process is waiting to be assigned to a processor. So there are so many processes that are running on your computer, and you know that the list is huge. I show you the list. So there are so many that are in ready state, meaning they are in line waiting for the CPU to give some of the resources to that process so the process can be executed. And they are waiting in line in orderly fashion until the CPU is available for them and the CPU can handle the set of instructions that are part of the process and can execute those instructions. So that is the state of the process in which they are in line, or that particular process is in line waiting for the CPU resources to be available to it so it can be executed. And finally, terminated. That is when the process completes the execution of all the steps that are part of the instructions that are coming with the process. Now, this diagram that I show you here is the cycle of activities of a process. So it all starts with being created under the new state of a process, then it goes into ready mode or ready state, and that is when it is in line waiting for resources to be available to it. And if the resources are available to it, then it moves to running state, so the actual instructions are being executed. Now when running state is being conducted, there may be an interrupt. And now we get into another concept, an interrupt. What does that mean? Another process that is classified as higher priority than the one that I am running is calling for the attention of the CPU. So an interrupt takes place, and that means my process is stopped because there is a higher priority process that is demanding the attention of the CPU. So my process that is a lower priority goes from running to ready, back in line. So now we are moving the process back in line because the CPU has to take care of something that is even more important than my process. And then from ready, whenever the CPU is available again, it will go back to running. And from running, if it completes all the instructions, it goes into terminated state. But it can also go into waiting mode or waiting state, and that is when, for example, you have a pop-up window that comes up on as part of the program that you're running, the process that you're running, and the pop-up window is asking for the user to say either yes or no, choose yes or no, click between yes or no on the pop-up window, because the process requires some user input as far as clicking of the mouse. So while the program or the process is waiting for the user to click either yes or no, the process will go into waiting mode. Why? Because the precious number of seconds that are taking for the user to click on yes or no could be better utilized by the CPU handling a different process. So your process that is waiting for user input in the form of the user clicking yes or no goes into waiting mode after being running for a few seconds, goes into waiting mode, so the CPU resources can be allocated to a different process. And now when that user clicks on yes or no, goes from waiting to ready, and from ready to running again until it completes all of the execution and it goes into terminated cycle step. So that is the life cycle of a process from new to terminated, and this circle can go round and round many times until it terminates with the final execution of all the activities of the process. It's pretty cool. Now you get to understand what the activities behind doors are when you are running a process on your computer. So really quick, let me take a quick peek at the virtual machine, and I'm logging on. So in the meantime, let me switch to the next screen. So scheduling queues. There are different scheduling queues that are part of the activities related to the management of processes on a computer system. So the scheduling queues that are important for you are the job queue and the ready queue. Those are the ones that are typically recognized by most authors handling the review of operating systems. However, I like to include the device queue as well, because the device queue is one important component of the scheduling queues, because you're going to notice that some of the processes are going into the device queue at any point in time because of the life cycle of a process. So the job queue is the one that we are going to talk about first. The job queue is when a process enters the system, they are put into a master list of jobs or processes that are going to be managed by that computer system. So as soon as the process is created, it goes into the job queue. All of the processes that are being part of the computer system activities will be made a member or a part of the job queue. Even if it is in terminated state, if it is in create or new state, if it is in running state, if it is in ready state, in waiting state, it will be part of the job queue because that is the master list of processes. Ready queue is the processes that are residing in main memory and are ready and waiting to execute when the CPU is available. So that is the line that I mentioned earlier as far as processes being in line waiting for CPU resources to be available to them. That is the ready queue. And then the device queue is another component that, again, is not always listed by different authors of operating systems theory. However, it is important to me because it is the list of processes waiting on a device to do something for them. The case of the printer that I described to you earlier today. So that process goes into the device queue because it is waiting for the printer to complete the printout of the document that you sent to the printer via the Microsoft Word program that you are running on your computer that has many different processes in the background running. So that particular process that is waiting for the CPU, for the printer to complete printing, is the one that will be part of the device queue. So let me see if I can do this. Okay, CPU scheduling. The CPU scheduling is the basis of multi-program operating systems. That is an important concept that I want to highlight to you. So by switching the CPU among processes, the operating system can actually make the computer system more productive and more efficient because it is switching the CPU resource among different processes. Now in multi-programming, several processes are kept in memory at the same time. So that increases the need for the operating system to be efficient in the use of CPU resources, and thus making the duties of the operating system even more important for you. When one process has to wait, the operating system takes the CPU away from that process and gives the CPU resources to another process. And this is a continuous pattern. So you see that your computer is always being used efficiently because it is moving the CPU resource from one process to another, while there are certain activities that are waiting for the process to complete. And that management, that order, that sequence of orders that are coming to the CPU, that are going to the CPU, is coming from the operating system. That is why the operating system has a vital function as far as allocating the limited resources of the CPU among the many different processes that are running on a system. So CPU and input-output burst cycles. CPU burst is when the process is being executed in the CPU. So imagine the process instructions that are part of the sequence of events that are making up the process itself. When those instructions are being executed by the CPU, that is called a CPU burst. On the other hand, the input-output burst is when the CPU is waiting for input-output for further execution. So the case of the printer that I mentioned earlier, in that particular case, the CPU is waiting for the input-output device for further execution before it actually moves back to the CPU burst. So that is the cycle between CPU and input-output burst. Now, the process execution begins with a CPU burst followed by an input-output burst, followed by another CPU burst, then another input-output burst, until the final CPU burst ends with a system request to terminate execution. Process schedulers. So we talked about CPU scheduling, and now we are going to talk about job schedulers. And the way that I want to make sure that you classify the process schedulers is the following. The first category is the long-term scheduler, which is called the job scheduler. And that scheduler selects the processes that are going to be brought into the ready list or the ready queue. So the job scheduler function is to select the processes that are going to be put in line, waiting for attention from the CPU in the ready queue. Next, we have the midterm scheduler, and that is responsible to swap inactive processes from main memory to disk. And that is important because the memory resources are also limited on any computer system. So whenever the memory is getting filled, the operating system makes the decision via the midterm scheduler to swap some of the inactive processes from main memory, the RAM, to the disk. Restore swap processes from disk will be placed in RAM on demand. So going back and forth will be handled by the midterm scheduler. Back and forth meaning from main memory, RAM, to disk, and vice versa. So that is an activity that is handled by the midterm scheduler. And then you have the short-term scheduler or CPU scheduler, and that is responsible to select the processes that are waiting in line from the ready list to run on the CPU via the allocation of CPU resources. So the CPU scheduler is responsible to take a look at all the processes that are waiting in line and selecting the ones that are going to be moved from the ready list, which is the waiting in line, to the actual execution of activities by the CPU. And then dispatcher is the kind of the doer within the CPU scheduler that is responsible to give control of the CPU resources to a process that is waiting in line. So it is the one that receives a PCB from the short-term scheduler and give the resources of the CPU so the execution of the code can be completed. Preemptive versus non-preemptive. CPU scheduling decisions may take place under the following 4 circumstances. There are 4 different scenarios that we are going to describe. The first one is when a process switches from the running state to the waiting state. Remember, we talked about the different process states here. New, running, waiting, ready, terminated. Those are the different process states, right? So the scenarios that are being described here are, number 1, when a process switches from the running state to the waiting state. Number 2, when a process switches from the running state to the ready state. For example, when an interrupt occurs, and we talked about interrupts being when a process is being interrupted because there is a higher priority process that is demanding the attention of the CPU, then my process that is a lower priority is interrupted by that call from the operating system. Number 3, when a process switches from the waiting state to the ready state, for example, at completion of input and output device steps. And finally, number 4, when a process terminates. Why are we listing these 4 different scenarios or circumstances? Why? Because the 2 in green, number 1 and 4, for situations 1 and 4, there is no choice in terms of scheduling. A new process, if one exists in the ready queue, the ones that are waiting in line for CPU attention, must be selected for execution. There is no choice. You must select one for execution, a new process for execution. However, in number 2 and 3, there is a choice that you can make. So when scheduling takes place only under circumstances 1 and 4, the ones in green, we say that the scheduling scheme is non-preemptive or cooperative. Otherwise, number 2 and 3, in blue, it is called preemptive. So that is the difference, and that is why we are listing those 4 different scenarios here on this table. Next, scheduling criteria or scheduling policies. This is the criteria or the policy that is used to schedule CPU resources or to schedule activities around the processes that are part of the operations of a computer system at any point in time. And those criteria are the following: CPU utilization, throughput, turnaround time, waiting time, and response time. So there are 5 different criteria that are used to schedule the processes within a computer system. Now, what are the algorithms or the formulas that are used to select different processes as far as the order of importance or the order of execution of processes? Because again, you have a huge list. I show you that under my task manager. How in the world will your computer know which process needs to be handled first? So it uses, the operating system does, it uses a scheduling algorithm, and there are many different choices between non-preemptive and preemptive, and we defined those earlier today. So for the first 3 that are non-preemptive, we have first come, first serve, shortest job next, and priority scheduling. So first come, first serve is easy to implement, is unpredictable turnaround times, and has an element of chance. So first come, first serve is not relying on the importance of the job, is more of an element of chance, because it is just grabbing the next process that is coming in line. Next, shortest job next minimizes the average waiting time. However, the disadvantage is indefinite postponement of some jobs, and it requires execution times in advance. Priority schedule or scheduling ensures fast completion of important jobs. So now we are classifying the processes and the jobs based on the actual importance of the jobs as far as which process is handled by the CPU first. Next, we have the shortest remaining time, and that's ensuring the fast completion of short jobs. Next, we have the round robin, provides reasonable response times to interactive users, provides fair CPU allocation. Then we have the multiple level queues, flexible scheme, allows aging or other queue movement to counteract indefinite postponement, is fair to CPU bound jobs. And finally, the earliest deadline first, which attempts to for the timely completion of jobs. So those are the different scheduling algorithms that are used by the operating system to schedule the execution of processes in a computer system, and they are divided in categories being non-preemptive and preemptive. This list is one that you need to keep in mind when you are taking your exams throughout this course. Now we are going to cover the first portion of chapter 5, which is process synchronization, and the learning objectives that we are going to cover as part of the first half are only two, 1 and 2. First, how system deadlock and live lock can happen or can occur, and number 2, how processes can become deadlocked. Number 3 and number 4, which are listed on the right here, are not going to be covered during this session. They will be covered next week, along with chapter 6, which is going to be the way that we conclude the process management review for our course map, the one that I showed you at the beginning of this presentation. For process synchronization, whenever there are multiple processes occurring, they may be accessing the same resources on a system, meaning the same CPU, the same memory, the same disk. I show you the resources when I open my task manager window, and you saw the resources being consumed by the list of processes. So there is a need to identify the order in which processes will be executed. And we show you how the operating system is handling that via the scheduling of jobs, right? So next, the processes can be categorized. There are two main categories. The first one is the independent process, that is the execution of one process when the execution of one process does not affect the execution of others, and the interdependent or cooperative process, and that is when the execution of one process affects the execution of others. Two processes accessing the same shared memory space is one example. And it requires, those interdependent processes require some type of synchronization. That is why process synchronization come into play, and that is very important as far as the orderly execution of processes. Now, what is a deadlock? A deadlock is a problem occurring when the resources needed by some jobs to finish execution are held by other jobs, which in turn are waiting for other resources to become available. A picture will describe this definition even better. So we have resource number 1 and resource number 2. Resource number 1 can be a file on your computer system, and resource number 2 can be another database record or another file in your computer system. Now you have many different processes running on your computer, right? I show you the list on my computer, and it was huge under Task Manager. So for this example, we are just grabbing 2 processes to make the example and the visual aid a little bit easier to understand. So we have process 1 and process 2. In this case, process 1 has already resource 1 assigned to it, meaning it has full rights over this file. But process 2 is waiting for that same file to be available, so it takes full control of that file. So process 2 is waiting for resource 1, but process 1 already has resource 1 assigned to it. On the other hand, process 1 is waiting for resource number 2. It could be a device, it could be a file. However, process 2 already has that resource 2 assigned to it. So this is a vicious cycle because you see the direction of the arrows, and this is creating what is called the deadlock state. How is that visualized by you, the user, when you are accessing your computer? So bringing the concept back to life. Have you been in situations in which your computer is unresponsive? You have 2 different programs, or maybe more than 2, open on the computer at the same time, and everything comes to a deadlock? And all you can do is reboot your system? Not only because those 2 programs stop functioning, but because everything else on your computer is unresponsive. So that is a good example of a deadlock state. 4 conditions for deadlock: mutual exclusion, at least one held resources must be non-shareable; hold and wait, there exists a process holding a resource and waiting for another. So this is depicted in this picture again. No preemption, resources cannot be preempted. And finally, circular wait, that is the vicious cycle that I showed you here in this picture. Deadlocks can occur on databases, on device allocations, on spooling, just being 3 examples that I am giving you. Finally, live lock, a lock system whereby 2 or more processes continually block the forward progress of the others without making any forward progress themselves. It's very similar to a deadlock, except for neither process is blocked or obviously waiting. Both are in continuous state of change. How is that visually reflected for you? You actually see the hard drive blinking on your computer. You actually see a progress bar or a progress circle moving on the program that you're running. So the 2 programs that are fighting for resources seem to be doing something. Your computer is not deadlocked, it's doing something, but it's not making any progress. So that is a good example of a live lock. So threads are too busy responding to other threads to progress. So even though something is happening, we don't get anywhere. So we don't get to the final execution of the processes or the instructions that are part of the processes. Overview: 2 processes pass over control of a computer resource back and forth without executing the process intent, thus not making any progress. Live lock can occur with disk sharing. Example: 2 processes waiting for input-output request. One process is waiting for information from track 20 on the disk, and the other process is waiting for information on track 310 on the disk. The ARM, the hard drive ARM on the disk, is moving back and forth between track 20 and track 310, back and forth, back and forth, back and forth, trying to execute the input-output request from the user. However, neither one is fulfilled. So process number 1 and process number 2 are not making any progress. Good example of a live lock. So that concludes our review of chapters 4 and the first section of chapter 5. Important takeaway that I want to highlight to your attention: reviewing this presentation is a must if you want to do well in the quiz that is part of the assignments for this week. So make sure that you review the full presentation, you keep everything in mind when you're taking the quiz, because you will do much better if you do that. So thank you again, and until next time.